Before addressing the stellar stage of helium flash, we now have enough elements to lay down some basic pentamorphic rules. We have already mentioned the notion of mass, and we recall that for each unit of mass of an atomic nucleus corresponds to the presence of 3 pentagons. For example, the nucleus of helium-4 is showing a mass of 3 times 4 units. This makes a total of 12 pentagons corresponding to the 12 dodecahedral faces.
Similarly, the boron 10 possesses a mass of 10 units and shows a form of 30 parietal pentagons.
Now let's move on to the second rule regarding electrical charge. We have seen that the primordial synthesis had given isotopes of hydrogen representative of the morphology of expansive foam. That is to say, an open but fragile pentamorphic structure under the conditions of stellar agitation.
Then, due to the shocks of the billiard synthesis, a modification of the meshing of the pentagonal scrolls is observed from helium to form a protective shell. The stellar nucleosynthesis then plays the function of a suck turnover for the structuring of the nucleus.
A separation takes place between the small internal volume of the enclosed nucleus and the outer space. This implies considering the electric charge as being bound only to the pentagons forming the outer shell of the nuclide while the interior remains neutral.
Thus, we can give a second pentamorphic rule. From helium, each unit of electrical charge corresponds to the sixth of the pentagon number exposed to the surface of the atomic nucleus. For example, for helium-4, with 12 pentagons arranged on the wall, we have an electric charge of 2.
Similarly with boron-10, where the 30 external pentagons give a value of 5 units of electrical charge.
However, only the pentagons of the wall are affected by the electrical charge while the inner pentagons are not. For example, the 3 internal pentagons of beryllium-9 are not counted in the electrical charge.
Likewise, the outer pentagons, not integrated into the nuclear wall, do not have an electric charge like helium-6 helices.
On the other hand, the parietal gaps have the value of electrical charge when they are placed in the protective wall, as is the case for helium-3 or lithium-6 and 7.
Now let us turn to the third pentamorphic rule, the notion of isomass.
We recall that the definition of the isotope corresponds to 2 atomic nuclei, which possess the same electrical charge with a different mass, as is the case for beryllium-8 and beryllium-9. Now we will see in the following chapters that some nuclides may have different morphologies with yet the same electrical charge and the same mass. Their isomasses such as, for example, beryllium-9, which has a trefoil shape and a second linear form.
Another example is given by boron-10, again with a trefoil shape, and another in linear form.
Of course, cases of isomassic morphologies are not the majority, but if some isomasses are unstable, we will see that others are stable and that this stability reveals its importance in some cases. And with these first three rules we can now describe the stellar stage of the helium flash.
First of all, in summary, we have the exclusive production of helium-4 during the stellar phase of billiard synthesis.
The small nuclides are transmuted in helium-4 by nuclear fusion, reversing their structure of meshing cycloid scrolls by turning effect due to shocks and radiations.
But the growth towards higher nuclides is halted because the morphologies of lithium, beryllium and boron are too fragile to shocks, and they go back to the much stronger dodecahedral structure, helium-4. It is as if any addition of new pentagons on the dodecahedral base was systematically peeled and eliminated to return to the original base of the order 5.
But bizarrely, it is observed in astronomy that the synthesis of heavier nuclides does not occur by the addition of elementary bricks, but by a direct leap from helium-4 to carbon and oxygen. And again, it is the analysis of pentamorphic morphology that will enable us to understand this phenomenon. Thus, during the billiard synthesis stage, we have a continuous production of helium-4 which remains inert to nuclear reactions thanks to its powerful dodecahedral structure. As helium-4 is relatively heavier, these non-reactive nuclides will gradually descend and accumulate towards the center of the star due to gravity. And, from a certain size, the giant star will be able to constitute a central core consisting solely of helium-4. And because of the high gravity and thanks to the non-reactivity of the helium nuclides of the stellar heart, this central element, composed of a unique element, will then structure itself into a gigantic solid crystal.
Thus, it is only from the basis of a critical mass permitted by a threshold of gravity that the accumulation of helium will then create a boundary between the mantle of the star and the plasma status, and its center becoming solidified. And it is at this boundary that the forces of friction will become so intense that the links of the scrolls of helium will then break.
It follows that this grinding effect will develop two types of bearing according per the speed of passage. At slow speed, the sliding takes place on a triangular basic network.
On the other hand, at high speed, the network is square.
Since helium is the essential element of this bearing, we are going to get two nuclear synthesis products. In triangular mode, during the low-speed border crossing, three neighboring helium nuclides come together and fuse to give, directly at one time, a carbon core.
And in square mode, with a rapid slip, four neighboring helium nuclides merge and give a nucleus of oxygen, also directly at one time.
Therefore, far from the classical representation of an unorganized mixture of protons and neutrons, we obtain simple but well-structured morphologies. With an electric charge of 6, The carbon-12 therefore has an area of 36 pentagons divided into 4 tetrahedral lobes.
And with an electric charge of 8. The oxygen core 16 shows a surface of 48 pentagons distributed in 6 lobes approaching the octahedral form.
Now, it is observed that some pentagons are slightly deformed to adapt to this new morphology. This means that the overall sum of the surfaces of the cycloid scrolls is decreased and that this reduction in mass results in a significant emission of energy. The temperature of the star will therefore increase considerably and the mantle will dilate enormously. The star in the phase of helium flash will therefore grow and become a red giant due to the presence of heavy nuclides. And for a few millions of years, the giant star will consume its helium reservoir to accumulate carbon and oxygen with a small percentage of nitrogen-14 and with traces of neon-20.
Now there are 2 scenarios. In one case, and we shall see in the next chapter, the star possesses enough mass to retain its mantle and synthesize the whole of the nuclides of average mass.
In the other case, the mass of the star is too weak, and the mantle is then ejected into the galactic vacuum. It's the birth of a nova.
After the explosion, the star retracts on a core composed mainly of oxygen and carbon. And since its ionized atmosphere is composed of neon, it will thus emit a white light.
It then becomes a small star called white dwarf, which will slowly cool down for millions of years.
White is white, Dylan is Dylan. White is